Thank you all for being here. So one doubt that you might have at this point is why Jordan, a guy that works in industry, also known as the real world, is giving a talk with someone from academia, which is sometimes called the fantasy land. So to tell you the truth, this talk will be about two independent stories, okay, that are actually sort of related and that they will converge in the end. But first things first. So this talk will be about data dissemination. And this is like a very classical distributed systems challenge where your goal is to have like a node propagating some relevant information to a set of participants. This might be a large number of participants. And then you have the requirements that you could expect from this. So you want the process to be reliable in the sense that all participants will get this relevant information. The process should be efficient because usually you have some other applications running on top of this and you don't want to consume a lot of resources with this. And it should also be scalable. So if your system grows, this mechanism should be working perfectly fine without any hassle. And so there are lots of applications that can benefit from data dissemination algorithms, like notification systems. If something is burning in your system, maybe it's a good idea to notify other components something is burning. You could possibly use this to stream multimedia content, and actually you can also use it for cluster management, but I don't want to spoil Jordan's part. In practice, when I was working on this several years ago, more that I want to remember actually, I was focusing on peer-to-peer systems that we all know it's a big thing nowadays. So data dissemination from the academic point of view, there have been proposed lots of solutions in the past. But I want to start very simple. So the simplest approach is if you have some data that you want to disseminate, just send it to everyone that is interested in it. So this is what I call a one-to-all pattern. So in a system with lots of nodes, if someone has information that is relevant to the other parties, he would simply send this message, this information, like point to everyone. So you see where this is going, right? And well, this is not completely bad in the sense that this is a very simple solution. It's very straightforward to implement. It's a for cycle. And it has no redundancy. So no node is required to be processing the same message more than once, which is actually a good thing. But on the other side, like, this requires every single node in your system to know all other nodes. And this might be hard if you have a very large system. And this is not really scalable at all, starting from the point that there's no load distribution here. We are putting all the effort of disseminating this information in the initial sender. Also, this is not really fault tolerant. So if one of these messages get lost, probably that process will never get this information. And even worse, if that sender crashes midway, then lots of processes will never get this message anyways. So, but I want to start by dealing with this problem of load distribution. So one way to deal with this load distribution issue is to organize all these nodes in a sort of a tree using some complex membership protocol. And then you simply forward this information across the tree. So this is the spanning tree approach. So basically you have all these nodes, you run some complex membership protocol here, and you define an overlay networks, this logical network connecting the nodes that forms a tree. And then if some process wants to disseminate information, it just disseminates information across the tree. And this is actually very efficient, so it's nice. And it has a nice diagram there. So the positive aspects of this is that you are effectively distributing the load across the nodes in your system. This is quite good. And you still have no redundancy here. So every process is receiving each message a single time. On the other hand, like managing these trees topologies is actually very complex. And doing it in a decentralized fashion is even more complex. And the other thing is that this solution is not really fault tolerant anyways. Because if during this process some node crashes, then the tree will probably become disconnected and some processes will miss the message. So to avoid this problem and to deal with fault tolerance, an alternative is for you to, instead of rely on a tree, just use some peer sampling service, basically based on gossip, I will talk about that later, that organizes the nodes in some sort of random, very highly connected graph, and then you flood this information across the links that form this overlay or this graph. So picking up again my blue nodes, you just define this random overlay with lots of connections, and then when someone wants to disseminate information, you propagate it across all single links of this overlay. The nice thing is that everyone will really get the message as long as this overlay is connected. So there are several positive aspects here. So we still have low distribution. Everyone is cooperating in this process. It's a very simple design, in fact, because keeping these random graphs is actually easy. It's not a process that incurs in lots of overhead. And this is robust. So this is fault tolerant because there's an inherent redundancy in this process. So each message is received more than once by each process. The negative aspect is that this is no longer efficient. Like forcing these processes to be receiving the same message and processing it will incur in significant overhead that we probably want to avoid. So we could actually deal with this efficiency issue by, instead of flooding the overlay with the information, using only sending the message to a subset of your neighbors in the overlay. And this is what we call gossip. So in this example, instead of forwarding the message across all links, each node will select 2 of these links randomly and then forward the message across them. And this is cool because with a very high probability, everyone will get the message. And some of the links are not even used, so you have less messages going around, and this is a cool aspect of the gossip protocols. And so you have low distribution in this design. It's actually simple because you're again using a random overlay. You still have some randomness there, so this is still fault tolerant. The problem is this is still slightly inefficient, although it's better than flooding. And this is no longer predictable, meaning that each message that you disseminate will traverse different paths, so nodes will receive information in weird orders, and this might be a hassle for some applications. So many years ago, I was thinking about how to address this issue of data dissemination. And well, I was not really concerned about this one-to-all. This is like the poor engineer's choice. But all these 3 solutions had interesting aspects, like the spanning tree was very efficient. But flood and gossip was very robust. It was really fault tolerant. And so what I really wanted to do at that time was to merge these nice properties into a single solution. And the thing is that when you start looking at these, you start obsessing, and then you start to see trees everywhere. And the fact was, when I looked at this pattern of flooding a message throughout an overlay, I started to see trees there. And I thought, well, maybe I'm going insane. But no, it's really there. There's a tree here. When you look at the pattern of messages, there's an implicit tree defined here. And the same is true for gossip. When you look at the pattern that leads to the first delivery of message to each process, there's a tree hidden here. So we had this nice observation that when you join all the paths that lead to the first message dissemination in any of these flood or gossip protocols, you'd have a tree. And so this was cool. And these observations have eventually led us to design a protocol called Plumtree. And we have this nice paper, and I should do a shout out to my nice co-authors, José Pereira and Luís Rodrigues. And those that follow Carlos on Twitter know that there is a bit more of story on this paper, but I will not cover that part of the story here. I can do it off record. But before I explain to you how Plumtree works, I want to say that I've been lying to you. So the gossip way that I showed you is only one of the more than 1,000 ways to do gossip. For this talk, I'm only concerned with two different gossip approaches. The first one is the eager push, which was the one I explained before. As soon as a node receives a message for the first time, it will select some random peers in the system and forward the message to them. And this is, well, as simple as you can get. But there's other approaches. One of them is to use this lazy push. In lazy push, when you get a message, instead of forwarding the message immediately to your neighbors, you just send a notification, an announcement saying, man, I have this message. If you want it, let me know. And then nodes that really want to receive that message will explicitly ask the message, and then the message will be transmitted. So you have to pay some extra latency here, but then if messages are very big, you actually save bandwidth, and this is a cool aspect of it. And so actually Plumtree, the name, comes from this combination of push and lazy push multicast. And we also have a tree there. So in fact, it operates like any gossip protocol in the sense that each node is gossiping with F other neighbors in this random graph. The protocol is fully decentralized, and this was very important for us at the time because I was working in peer-to-peer systems. You don't want to have centralized components there. And the fundamental idea here is that we are creating or allowing a tree to emerge from this gossip dissemination process that we then leverage to disseminate all other messages. And we actually combine this eager push and lazy push. That part is obvious. I should also say that in this work, we were assuming that we had TCP connection across all nodes. This was good for both reliability of the communication, and we actually leverage it to detect faults. So the intuition here is that we define the tree using the links that were used to transmit messages that resulted in a delivery to the upper level to the application, basically. And so our approach here is that when the system bootstraps, we assume all the links in the random graph are part of the tree. This is clearly not a tree, but we assume that. And then whenever a redundant message is conveyed through a link, we mark that link as being outside of the tree. And we still use that link. I'll explain how. And by the end of your first broadcast, you basically have a tree. If the graph is connected, it is ensured that the tree you have defined by this process is actually covering all nodes in your system. So the idea is really simple. You have this random graph. Someone starts transmitting the message. All these links are still part of the tree at this point. And you start transmitting. If the message is received by some process, it's not a repeated message, then this link is fine. When redundant messages start to being transmitted, we start to mark these links as redundant and removing them out of the tree. That's the dashed lines there. Well, these links are still used because on the links that form the tree use eager push. So whenever we get a message, we immediately push the message throughout these links. But on the other links, we use this lazy push. So we are still sending announcements there stating, man, I have this message. If you really need it, let me know. And this is actually the base for our recovery mechanism. So this is what I explained before. It's the process to deploy the tree, but then we have a recovery mechanism. And so basically, as you can imagine, if some node fails, then the tree will break for sure, except if this was one of the nodes in the end of the tree. And then when the tree breaks, some processes will no longer receive messages, which is a hassle. But they still receive, with a high probability, these announcements saying that these messages are still being transmitted. So whenever a node receives a message, an announcement for a message that it doesn't receive after some time, he explicitly asks this message to that peer by saying this graphed message. And so this graphed message has a dual purpose. First, that peer will receive the message he missed, but also that link will be added to the tree. And by the end of this process, lots of nodes are recovering the tree independently. So in the end, you might not end up with a full tree, but with a redundant graph again. But the nice thing about this protocol is that the next time you transmit a message, then these redundant links that were added during recovery will be removed again. And so you end up again with a tree. And so we did some experiments with this. You know how our scientists, we love graphs and plots and numbers. And so we had lots of simulations experimenting with this protocol, and we actually compared it with a simple gossip, a push-based gossip protocol we called Eager. And we actually had several configurations of Plumtree here with multiple senders, and there's also an optimization of the protocol that rebalances the tree during the execution of the system. And so the first result I have to show you is like this relative message redundancy, which shows, in average, how many unnecessary messages are each process receiving and processing. And so the red line upstairs shows what gossip gives you, like you're receiving lots of redundant messages and spending lots of resources on it. With Plumtree, independently of the number of senders and independent of if you are using or not our optimization, you never receive redundant messages in steady state. Actually, a nice thing about this is that when there are faults in the system, the line for the gossip will go down, and the line for Plumtree will go up slightly. Then Plumtree will immediately recover and go back to zero. Another aspect that we evaluated was how much time were we taking to disseminate information across all participants. And we measured this by seeing how many hops a message had to do in this overlay to be delivered to everyone. And so actually when you use Plumtree, either optimized or not with a single sender, we are basically equal to gossip, which is good because gossip is actually very fast to converge, except in some, weird cases. And when you use multiple senders, as expected, this takes longer to converge. And this is because if someone is transmitting a message through a tree where he is like very, very far away from the root, the message has to do extra hops to get to the root and then being disseminated. Actually, our optimization could sort of mitigate this problem. And finally, there's the question of fault tolerance. So how many nodes in our system could crash while we're still being able to deliver messages to everyone? And the results show that even if you have like half of your system crashing at the same time, you still had almost 100% delivery rates in the system. Well, things start to get worse when you have 70%. I should tell you that this plot actually shows what happens when you're not recovering the tree. When you are able to recover the tree, then these numbers are clearly much more higher. So this stops the first part of my story. I will handle it now to Jordan.
All right. Thanks, Joao. So, like Joao mentioned, this is sort of two parallel stories that are going to converge at the end. So you're going to hear some similarities. I'm going to point some things out, but this is the story of RIAK now and our work in cluster metadata management. So we have this need for information globally across a cluster that is needed locally on every node. It's information that we use to make decisions about where to send requests, who owns what nodes are in the cluster, what data needs to go where. And these aren't things that we can go over the network for in the typical case to answer these questions for. It would add too much latency overhead. We also want to store configuration, like how many replicas you have of your data, what backend you're using, what features you're using. And then we also want to monitor this system. So not only monitor RIAK and what it's doing, but monitor the actual metadata subsystem itself. And so have this sort of self-hosted monitoring. And so we have some requirements. First and foremost is failure tolerance. So we just added in RIAK 2.0 the ability to have sort of roles and auth similar to Postgres. And for example, if you have a malicious client, you've identified him, some of your nodes are down, you should still be able to stop that client from using as many nodes as you can. And so we need to be tolerant of failures. We can't say, no, you know what, we have to let him keep being awful because 3 nodes are down. So we need to be failure tolerant. Another good example is if your nodes are failing, we still need to be able to add nodes. We don't want to tell you, no, sorry, everything's going by the wayside and you can't do anything about it. We also want to have this information converge around the cluster as quickly as possible. So we want to be aware of new nodes. We want to keep monitoring data as up to date as we can. We know it's not going to be perfectly recent, but the closer our numbers are to now, the better. But this is also a background process. This isn't RIAK's primary function. RIAK is a key value store, and this is a background subsystem. And so we can't slow down foreground work, and we can't use your resources. We can't be wasting the network, sending about a bunch of data because you actually need that to send around your RIAK objects. And then lastly, we, again, for some of these sort of naturally fall out, that we prefer to be available over consistent. In the case of partitions and failures. Rarely, in a few cases, do we need CP, and that could be a subject of a whole other talk about how we hackily lay CP on top of AP systems. But for the most part, the majority of the stuff we store in this system is AP. So what does this look like in RIAK? Again, you'll see a very similar story. So RIAK has gone through 3 different metadata subsystems in 3 major versions. So there's 0.x, 1.x, and we just recently released 2.0. So the first version, as I hear it written on a plane, is what we'd call from the seminal paper on gossip called classic anti-entropy protocol. So this is each node picks a couple random nodes. It basically exchanges its entire state. They compare some state. They figure out the differences. And we keep kind of going on this random path until everybody learns about the data. And we have sort of this separation in RIAK of this idea of who's in the cluster or the peer service and how we actually send the information. And so we did this the same way. So not only who was in the cluster, but everything, all this configuration information, everything was all in one big blob, and we just randomly gossiped it around. In the 1.0 series, we wanted to make a few changes, and I'll talk about why momentarily. And so we added a static graph, and we did the flooding that Joao mentioned. And again, we use this same idea for data dissemination. In 2.x, we kept that system for a very small subset of data, the peer service, and who's in our cluster. But the actual data dissemination, we moved to using sender-based embedded trees a la Plumtree. And so why did we sort of make this progression? So anti-entropy is very reliable. We always know that our data was eventually going to get there, but it's slow to converge. And so when you're adding new nodes, for example, which is really the biggest driver here at the time, you want to know about them as fast as possible. And it was just taking too long. So we want to improve convergence time, specifically also when things are failing. And so the static graph, the flood, does that for you. But that has a lot of issues because the flood is extremely redundant. You send way more messages than you need to for that convergence time. And we realized along the way that actually that really fast convergence time it was really only important for a small subset of the data, which was that membership information. And the rest, we could tolerate slower convergence time for less redundancy. And then also, this was a bit of an implementation detail, but as I mentioned, we were just sort of like shipping the state around everywhere, and this is similar to a lot of other subsystems that do gossip. And the problem is that we're sending information that every node already knows. In the literature, this is called cold rumor mongering. And so we wanted to fix that as well. Our goal was to improve resource usage and improve stability. So the story of how I found this paper is Joseph Blomstedt, who's been at Basho a much longer time than me. Actually, today, I forgot to mention, is my 2-year anniversary at Basho, by the way. But so Joe wrote up a very forward-looking write-up of some of the future of RIAK, and some of that has actually come to light today. And part of that was he mentioned this Plumtree paper. And so I spent a lot of time reading about gossip and finally arrived at Plumtree and was like, oh yeah, this is something that will help solve our problems. It's clearly like we have these problems that they're talking about. I can see it in practice. And so we started looking at what it would take to implement it. Because if you've ever worked with an academic paper, while they are clearly solving very hard problems, taking that to practice is a different step. It's not like, there's not a prescription. There's a lot of things you have to fill in. And so we had some different requirements in a different sort of environment than Joao did in peer-to-peer systems. For starters, this idea of connectivity. So Plumtree says that all nodes should have in their partial views another correct node. And so that's that every node should be able to talk to at least one other correctly functioning node at all times. And in RIAK, we can't actually provide that. You need to, if one node is partitioned from the rest of your cluster for 2 days, we still need to be able to take any data you wrote on that in the metadata subsystem and propagate it everywhere. It's not acceptable for us to fail in the case of isolated network partitions. Our system model was also, we wanted it to be a little bit stronger. So as Joao mentioned, Plumtree assumes TCP. And while we actually have that in Erlang, some of our potential future uses meant that we didn't want to assume that guarantee. And so we wanted to consider at least drop delayed and duplicated messages. Duplicated, we were less compared to dropped and delayed. And in addition to the node failures that they were exploring. We also had some things that were working in our favor that they didn't have to deal with in their environment. One is that our peer service is fully connected. A RIAK cluster is not typically on the order of 10,000 nodes in production. The average clusters range from between 5 and 100 nodes in one single data center, which at the time this is all we applied it to. And so we have a different level of scale in our peer service than they do, and so we can make some trade-offs there. Additionally, Plumtree's membership was reactive, that when a node failed, the failure detector would notify the system of a node failure. And in our case, the failure detector in RIAK lives a layer above this subsystem, not within it, as is typically the case. And so we have more operator-controlled membership, where an operator, notices this node is completely useless at this point or something and marks it as down or removes it from the cluster. But if a request is routed somewhere, is that node down? It's a wholly separate layer that we can't use that was available in the Plumtree system. But actually, it makes certain things simpler for us as well because of how nice the algorithm is in terms of rebuilding the tree in almost any case. So we had to do some things to deal with these differences. The first one was, again, we want to deal with dropped, delayed, duplicated messages. And so these messages that healed the tree, they were sent out once. And if you drop them, no more tree healing for you. And that was because, again, their system model was about fail-stop node failures. And ours was different. And so what we did is we extended the protocol that when you send a lazy message, you keep it in a set. And we added another message that if you've seen that data, instead of ignoring it, you just send back, hey, I've seen that, I don't need it. So it's a very lightweight additional message, and we prune the outstanding set. So we keep a nice bounded set, and only in failure cases does that grow momentarily until things heal. And then also the natural act of saying, oh, actually, I need that data also acts as an ACK. So by extending it, by just adding the set and adding one message, we were able to deal with more of our system model. Also, as Joao showed that extreme failure case that as you hit 70%, that the protocol started to fall off in terms of how correct it was in delivering the messages to every single node. And in RIAK, our metadata subsystem, first off, needs to always eventually Every update needs to always eventually reach all nodes, regardless of failure. And additionally, new nodes that join the cluster need to be made aware of the current state of the system in some way, which was not a requirement of the original paper. And so what we do is, because we have this nice property that our peer service and our scale is a little bit smaller, is that we back it actually by a classic anti-entropy gossip again. It's not the original one, it's a different one based on Merkle trees, and it's a little bit more complex. But we use that in these extreme cases to fall back on, okay, well, in the really bad failure cases, we'll fall back to the, very redundant but safe thing. And so we get sort of the best of both worlds. Got a little light in my eyes there. So the last change or implementation detail that we had to do was, as Joao mentioned, if you saw that jagged graph at the top where he had multiple senders, where the idea is that the tree is optimized for the root, for the original sender that sent the message. So if you start sending from other points on the tree, from either the middle or from the leaves, you get less predictable and often less efficient convergence. And so since in RIAK, typically you put a load balancer in front of your cluster, you update some configuration, your load balancer picks a random node and does it, we didn't want that variability exposed to users. And so instead, we have a tree per every node in the cluster, where every node is its own root, or every node is the root of its own tree. And so when you send a message from node A, we use its tree, and when you send a message from node B, we use their tree. There's some overhead in maintaining this, but what we do is we construct these trees lazily. So if you never actually send from a node and it's only participating in receiving messages, then we never construct a tree for it. And so typically this keeps things down, because even with the load balancer, most people don't end up talking to every node because they don't update configuration that often. So was it all worth it after all this? So actually, it's not actually a lot of code. Took about a month. Erlang makes a lot of these things really nice. But was it valuable? Well, the numbers say yes. So it wasn't actually our original goal to reduce convergence time. Again, as I was saying, we were okay with actually being less convergent in terms of speed at the cost of, in terms of being less redundant. But we actually kind of got both. So we reduced convergence time, measured in what Joao described as the last distance hop, or how many hops does it take to kind of get to the leaf nodes. And we reduced that by 66%. And then we reduced the needless message, or the redundant messages, by 99.999. There should be a bar, but Joao made me lose LaTeX, and I don't know how to do that. And the reason it's not 100%, the reason it's not 100% is because the implementation, there are certain races where you can, even in the stable state, sort of tweak the tree, and you can get maybe like one redundant message when you shouldn't have. And so, in practice, we don't make ridiculous claims. So 99.99 bar is going to be as far as I will go. And then the other thing we wanted to measure was where was our percentage in comparison to the research in terms of when we needed to rely on that anti-entropy protocol. When did Plumtree reach that point where it was failing to disseminate the messages to all nodes? And for smaller clusters, this looked really good. And we were like, yeah, they're 70%. We're near 90. Like, that's awesome. And as we started to get to bigger clusters, that tapered off really fast. And so it got all the way down to 45% as we started to get up to 40 nodes, and 40% as we got up to 80 nodes. And so we wanted to address this before we put things into the hands of our customers for RIAK 2.0. And so this led to sort of tuning that layer underneath what we call the peer service, of how we find out which members potentially could be our links in the tree. And so it turns out that the fan out of the initial tree, or how many peers, how many branches you have, initially really matters. And so with some testing, we found that for clusters of greater than 10 nodes, our fan out, instead of being 2, as it is for anything smaller, is now the natural log of the cluster size plus 1. So you plug in 20 nodes into that, and that's the fan out for the tree. And we were able to raise things much closer to the paper, around 70-80%, until we need to rely on the anti-entropy to work to save us. But as we'll sort of get into as we transition back to Joao, is that with our use of multiple trees, that idea of sender-based trees, there's going to be more tuning we have to do, and that's going to be the subject of our future work that we're going to be looking at.
So meanwhile, on the other story, last time we talked, I was very happy. So we had published Plumtree. This was efficient. It was robust. It could even rebalance itself when you had like this optimization in place. So we should be very happy at this point. The reality of it is that I've been lying to you. Trees are not that great. Trees have this inherent problem where it doesn't really distribute load evenly among processes. So to show you why, like imagine this tree, very cool and all that, but in this tree, only these 4 nodes are interior. Only these 4 nodes are effectively forwarding messages. All the other guys here are basically just receiving messages. They are not actively collaborating in this dissemination process. So at some point we started, okay, we have to solve this problem. And like the obvious solution seems to be, well, just create more trees. You create more trees and you'll see that the load will become distributed evenly. And so we thought, how hard can this be? And so we came up with these 2 naive solutions that were actually based in some works from the academics literature that we named nuts and bolts. I don't want to tell you the effort that it was to make sure that these would be the names of the protocols. And so basically what we did here is that in nuts, our idea was, okay, so you have this random graph, right, that is provided by the peer sampling service. And if you want to deploy, let's say, 2 trees, you just pick up 2 random nodes here, and you allow each of these nodes to deploy a tree using Plumtree, regular Plumtree. And if you are really lucky, then the trees will be very efficiently deployed, and nodes will be participating evenly in both of them, and so you have a better resource usage. Preview, it's not true. The second idea was to go the other way around. So instead of using a single unstructured overlay, we could deploy 2 overlays, for instance, if we want 2 trees. Because these overlays are random, the links will be completely different. And so if you deploy 2 different Plumtree instances, one on top of each overlay, then with some luck, different nodes will be interiored in different trees, load will be balanced, we'll be happy. This is not true at all. So we ran some experiments using these nuts and bolts, and this plot shows the number of nodes that are interior in 0 trees, 1 tree, 2. So we are deploying 5 trees in these experiments. And what the results show is that actually there are lots of nodes that are interior in 2, 3, and 4 trees. You have even some nodes that are not interior in any tree, despite the fact that you have 5 in place. And some are even interior in all of them. So we didn't got to load balancing at all with these nuts and bolts. So we went back and we tried to think how we should address this. But the first things first, why is it so important to have nodes being interior in a single tree? So I have already explained from the point of view of load balancing, but there are other aspects. One of them is that you want to use resources that you have available in your system. And for that, you should ensure that at least each node is interior in a single tree so that it contributes to the process. But on the other hand, from the fault tolerance point of view, you want nodes to be interior in the minimum number possible of trees. Because if you have a node that is interior in all of the trees and this node crashes, then you're screwed. All of your trees are going to fail and information will not flow. So this is why we really want to ensure that each node is interior in at most 1 tree. Exactly 1 tree, actually. And so this led to the design of this Thicket Protocol. Again, I had very nice co-authors that were Mário Ferreira and Luís Rodrigues again. There's no story in this paper, I think. And I don't have time to explain all the details of this protocol. That would be like a talk on itself. But I can explain to you the high-level overview of how this works. So the principle to deploy these trees is similar to that of Plumtree, with the exception that in Plumtree, we started the system assuming that all links were part of the tree. In this case, we no longer do that. We add explicitly links to the trees, and we do so being aware that there are other trees being deployed. This is important to ensure that only each node will be interior in a single tree. So there's quite a challenge here to find the minimal coordination that you need to make sure that you achieve this goal. And because we didn't want things to be centralized in any way. This is fully distributed again, the algorithm. So, but we sort of found that minimal coordination, I believe, and the paper actually explains this in more detail. And another thing that differs Thicket from Plumtree is that in Plumtree, when you broadcast a first message, your tree will cover all nodes as long as the graph was connected. In this case, this is not true. This might be related to the fact that this is probably an NP-complete problem, so I think it will be hard to get there. So, but when you basically build these trees, they will not cover all the nodes. But fortunately, we have all these recovery mechanisms that we had in Plumtree. And so the recovery protocol here is the component that makes sure that your trees will cover everyone eventually. And this is actually achievable in a few rounds. But for this mechanism to work, and in sharp contrast with Plumtree, we had to add some additional information to the messages we were announcing in this lazy gossip fashion. So we had to take note of how many trees each node was being interior in, what was that node load, all that sort of things. And so instead of doing as we did in Plumtree, where we recovered the tree by picking the link that had the lower latency, we here have to take into consideration all these things. What are the positions that each node is in each tree? And then we use this information to pick up the best node to repair the tree. And so again, we like these experimental results. So I have some experimental results to show you. And so this plot I already showed part of it before, shows the distribution of nodes in interior positions across the trees. I also have a line there for Plumtree with a single tree, which is a purple line. And so in Plumtree, as you could expect, like only 20% of the nodes were effectively forwarding messages. 80% of the nodes were just there receiving messages and doing nothing. And actually, in Thicket, in contrast with nuts and bolts, we actually could improve this significantly. So almost 90-something% of the nodes were actually interior in a single tree. For practicality, some nodes are also forwarding messages in 2 trees, but, well, again, this is NP hard problem. So if someone tells you that they have a decentralized solution that doesn't have this effect, you should think that you should not take this word at face value, please. So finally, we had this issue with reliability. So now we have all these trees. How reliable is our system? And experiments actually show, and in the x-axis we show the number of nodes that are failing continually. And so actually we were still reliable. So we were close to 100% delivery rate, which was cool. Nuts and bolts were actually much more sensible to faults than Thicket, and this is because there were some nodes in nuts and bolts that were interior in all trees. So if one of these crashes, then all of your trees are broken simultaneously. And I should also mention that we were using a trick here, a dirty trick here, because we were using network coding across all the trees. So even if one of the trees was unavailable for a short amount of time, information would still be propagated across the cluster. So there's that. And so this concludes my story. I will let Jordan tell you the rest.
All right, so we'll take you through the end, which is so as we started to talk, sort of the story about how Joao and I met is that Russell and some of the CRDT folks went out to Braga and were in the office with one of Joao's co-authors. And so we started speaking, and we decided to do this talk, and he sent me Thicket. So we started to measure, do we have this problem? So again, because we have multiple trees, we have n trees, the number of nodes in your cluster. So it would be logical that if, let's see if this research holds. So for 10 nodes, things looked pretty good. So we're never, because of the number of trees we have and the number of nodes and the fan out that we want, going to maintain a single tree like Plumtree was. But we do want to maintain a very tight, low variance in the numbers. And the way I sort of think about this is kind of like our goal with consistent hashing in terms of load distribution. We're going for the same goal here of every node should participate as equally as possible. And so for 10 nodes in our tests, things look really good. So we get up to 20 nodes and 80 nodes, things start to look like the research. So for 20 nodes, we see that, or actually in both cases, and I think this has to do with how we pick our initial trees, but I haven't proven it yet, 4 nodes are interior only when they are the roots. So only when you send information there are they interior. However, in the 20 node case, the other 16 are interior in 5 or more trees. And in 80 nodes, 36 of 80 are in a quarter or more of the trees in the system. So we have this huge gap in the middle. We have some nodes doing almost nothing. We have some nodes who are mostly leaves, and we have some nodes who are doing a lot. And so in RIAK, we don't want that to be showing in your latency of, oh, well, I'm doing reads, for this key space, and I happen to be on the nodes that are interior in a bunch of trees, and now my latency is affected. And so this is an area that we're going to be focusing on. And so one of the things, as I mentioned back when I was talking about the peer service tuning that we're going to have to go back and look at is, can we get some quick wins again by tuning how we deploy the initial graphs? And just like we did for increasing the percentage of failures that we could tolerate, we know that there's this tight coupling between the fan out, the number of trees, and how many times the node must be interior. And so there are some things we can do to basically shorten the height of the initial trees and increase the fan out that should hopefully end with at least a better story than what we have now. But we have some future work to do because we want to start using this system more. And so probably our biggest area in this is going to be exploring Thicket, and again, going through the process of how do we take this academic paper with its system model and its assumptions and adapt it to ours and what's practical. And so there's a lot of work to be done here in terms of how we implement this and how we migrate the system, because we are going to have this running in production by the time it's done. And also, looking at, are there other solutions? And the reason that we want to do this is because I lied a bit earlier when I said that we just use the peer service for membership data now. We want to get there. Again, we have production systems, and that means that I can't just take your data, move it somewhere, and not give you a path to upgrading. So that we are slowly migrating this data from the 1.x to the 2.x subsystem, and we want to store data we couldn't before. So as we start to use this subsystem more, and we want to start putting more rapidly changing information through it, like monitoring, we're going to need to go back to Thicket and fix this problem. And so that's going to be one of our biggest focuses. The other big focus is, and one of the reasons we originally built this, is that we knew that over time, well, I shouldn't say that. John knew, I didn't know, that we'd end up using this globally. And so the idea here is that we want to scale this much past the 100 nodes in a single data center of RIAK, but across a globally deployed version of RIAK where there may be multiple 100 node clusters, all disseminating information globally. And there are some things we have to do there, like abstract out both the peer service system and the messaging layer. So there's some more just sort of engineering work here. And hopefully we will sort of fold Joao back in to that. And that sort of leads to our conclusion, which is things have gotten better the more we've communicated. So as you can see, we're kind of, we converged right before Thicket, basically, and we're starting to, sort of see not only the academic feeding back into the practical, but us feeding back into the academic. So while we've largely followed the academic research, until recently it was inadvertent. And especially because the research was kind of on a different field. But now we've begun to work together, and so you will see Joao working with us and advising on how we deploy Thicket in RIAK or some other system, and you will see me working with Joao to publish papers in the academic area around some of our work we're doing with RIAK and how that feeds back in. So that's our story. Thank you very much. Again, I'm Jordan, this is Joao, and we'll take questions.
Good point, yes. Okay, in this research, we were assuming that links had the same cost. But I think that's actually easy to integrate in the protocol. You just have, so as I said, when we are repairing and selecting links, we were mostly concerned with latency. So the one that gives me information faster is when I pick, but I can tweak this as we did in Thicket. I can tweak this algorithm and select using other criteria. So I think this is easy to integrate.
And if I can follow up on that a bit, depending on what you mean by cost, but in two ways I can sort of answer this is, one, the protocol actually optimizes for the fast path. So if the cost is more, I have a slow link, the protocol actually naturally, because the slow link will typically deliver the redundant messages, will naturally prune it out. And then the other constraint is actually as we go to WAN replication, we have a very specific topology. We have constraints about where data can flow and things like that. And so it's not about cost, but it's actually about sort of having another layer of overlay, right, where we have to overlay on something more restrictive. So those are areas, that's part of that WAN replication area that I was talking about. But yeah. We'll go to this side of the room and then we'll come back. So for the peer service, you have a choice. You could have a centralized one. In Joao's paper, it's his previous work, which is HyperView, which is a fully decentralized gossip-based peer service. In RIAK, we're using our gossip-based, that static overlay kind of flood for the membership. And so, yeah, both are decentralized. But it's, I like to make that separation between where do you get your nodes from for the tree and then actually building the trees, because you can plug in different ones. So.
Okay. Okay. So I would say that, like, looking at Plumtree only, if you really have only a single tree, you are going to pay this cost. Okay. If you are sharing a static tree that only adapts itself and you have some faults going on, depending on your workload, our optimization, the one that I actually didn't mention, could help you. Because in our optimization, when you switch the sender to some other point, the tree sort of reconfigures itself to optimize latency for that sender, so that the new sender becomes the new route, you see? Using Thicket, yeah, you could deploy several trees, and you'll have this benefit of having loads being distributed evenly across all processes. If you deploy these trees in a careful way, you could actually avoid to have a single tree per sender, and then have like routes scattered across your nodes, so that you could always have like a proxy route that you could contact directly and ask, disseminate this for me, and then distribute this load across the routes. That would be the design choice I would make. But maybe Jordan has...
No, I was going to actually say the same thing, right? We went to one extreme where we did sender-based because we knew our cluster size was pretty bounded. And again, that may change as we move to WAN replication. And I think what Joao said is spot on. Of, you know, you can strategically choose a few routes, or you can just go with one. And the optimization, again, it basically adjusts for noticing that links are either like there's too much height in the tree, basically, and kind of compacts things. We have time for one more question. Looks like we're good. Oh, okay.
Is there maybe some room for practical optimization, like using multicast for discovery?
So using...
Right now, like, nodes going down, and node notification looks like it's all unicast per node.
Mm-hmm.
Maybe there's some room in there, perhaps. I don't know. You had all thought about that, or?
I haven't.
I haven't also, but I would say that yes. Well, as Jordan was mentioning before, when you have like these high latency links between different clusters or so, you might want to use hierarchical approaches. So if you model this as a different hierarchy of the service, maybe, yeah, there's some space there to use it, yeah.
Yeah, it'd definitely be interesting with chatting with you
Yeah.
about it afterwards.
But I would have to think about it, yeah.
All right. Thanks again, everybody.
Yeah. Thank you, guys.